Hello and welcome to this video on limits. This is the first part of several videos that I will go through where we go through an overview of how to evaluate a limit. It's easy to know what to do when you're in each section of the text where it says, oh, we're evaluating limits by doing this. We're evaluating by, limits at infinity, limits that go to infinity. But how do you start a limit problem when it's just find this limit? And how do you continue through for all the different types you might find? I'm not sure I covered all the different types, but I covered many of them in this series of videos. So here in part one, we're going to talk about limits that approach a number. And by that, I mean a limit as x goes to, as you can see down here, -3, for example, would be an example of a limit that approaches a number. Now that's in contrast to a limit as x goes to infinity or negative infinity. I'll do those in separate videos. But for right now, here you're presented with a problem. The first thing you try every single time is direct substitution. So by that I mean pretend this was a function. That's maybe not great math language, but you're going to replace the x in the problem with the -3. So you want to do that with careful order of operations. By careful order of operations, you see here I have the cube root of x plus 2. We're taking the limit as x goes to -3 of the cube root of x plus 2. So I'm going to replace the x with a -3. Notice when I replace the x, I put it in parentheses. It's not particularly important that I do that in this problem, but in other problems where you're raising this negative number to an even power, it becomes important, especially if you're using a calculator. You make mistakes otherwise. So I suggest putting all your replacement values for x in parentheses. So a radical symbol, like this cube root, acts like parentheses. So the first thing I do is I do a -3 plus 2. The signs are different. The difference between 3 and 2 is 1, the 3 was bigger, so I get a -1. -3 plus 2 is -1. So now I have the cube root of -1. So the answer to that is -1 because a -1 times a -1 times a -1 is indeed a -1. -1 cubed is -1. You could do that in your calculator. You don't really need to. I should hope you don't need to. So your answer is -1. The limit as x goes to -3 of the cube root of x plus 2 is -1. So for that example, direct substitution worked and you're done. Now let's go on to another type of problem where maybe it doesn't work. So in example 2, here we have what we call a rational function. It's two polynomials divided by each other. In this case, a quadratic, degree 2, and a linear, degree 1 polynomial. We are asked to evaluate the limit as x goes to 2 of negative, note that negative number there, negative sign, sometimes we miss those, of x squared plus x minus 6 all over the quantity x minus 2. The first thing we try is substitution. And you can see right here, I keep the negative sign, don't lose that negative sign, but I'm going to replace all of my x's with 2's. And for the most part, I should have probably put a parenthesis around this instead of around that. But for the most part, I put my x's in parentheses. If it's a positive number, that's not as important, but it is important when it's a negative number many times. So when I square the 2, I get 4. 4 plus 2 is 6. 6 minus 6 is 0. I get a 0 on the top. And 2 minus 2 is 0. I get a 0 on the top and the bottom. And I do have my negative sign there, but there is no such thing as -0. The answer here is 0 over 0. It's not 0 because you cannot divide by 0. This is a problem. If it were 0 over 5 or 0 over any number besides 0, your answer would be 0. You'd be done. But you're not here because you have division by 0. Because 2 is not in the domain of this expression. If you put 2 in the denominator, you get 0. You happen to get 0 at the top, though. So this requires us to use a different technique. We'll look at this one again when we go to step 2. For this one, we're going to end up factoring and reducing, but we'll do that later in step 2. So moving on to our next example, We're going to try substitution in each of these. So if you have a problem like this, example 3, here's the other thing that could happen when you try substitution. If the limit as x goes to -2 of x squared divided by the quantity 2x plus 4. When I substitute, now notice in this case it was very important that if I'm using my calculator, particularly -2 goes in parentheses, because in your calculator, -2 squared is actually -4. Does the exponent first and then applies the negative, because exponent's come before multiplication or before subtraction. It's not really subtraction, it's multiplication. But if you do this, that's -2 squared. That's what you want. That's 4. You want -2 times -2. This one here is the negative of 2 times 2. So that's why it's important to put this in parentheses with an even exponent. But here you notice I get a 4 divided by 0. The division by 0 still means I can't evaluate. But the fact that it was a 4 divided by 0 tells me my step 2 I'm going to do. It gives me some clues as to what to do in step 2 as well. So example 4. So you move down here. This is another one. The limit is x goes to 1. When I put 1 in at the top, I get 1 minus 3. I actually get -2 divided by 0. This should be -2 divided by 0. So I need to go to step 2. I get 0 on the bottom again. I'll need to go to step 2. I will do both of these out in step 2. But so substitution is not working for a lot of these, but it is important that you try it first. That's why I did these videos in this order. Example 5, everybody's favorite, trig functions. Make sure, if you need your calculator to do this, and I hope you don't, make sure you are in radian mode. But when I do the substitution, this is the sine of 5x, right? So if you're starting to think it's multiplication, read this. You have to take the sine of something divided by 3x, and we want as x goes to 0. So if you actually do this in your calculator, which I hope you do not, you want to do this. You want to do sine 5 times 0 divided by, and you want to put the bottom in parentheses, 3 times 0. If you don't put the bottom in parentheses, you will divide by 3 and then multiply by 0, and you will simply get 0. But you will get undefined. And if you do this in your calculator, you're going to get undefined or error. What you should do is if you want a clue as to what's going on, find the sine of 5x, evaluate that, and evaluate 3 times 0, and see you get 0 over 0. This, we will look again at step 2. So all of the problems that didn't work for substitution came up with some number divided by 0 so far. There are other things that could happen that could send you in a different direction, but I'm trying to hit the major types of problems you're going to see. So that's substituting, and that only worked for one of my. Example 1 is done. Substitution worked. So if I got 0 divided by 0, so direct substitution did not produce an answer. What if I got 0 divided by 0? Well, that's case 1. Example 2 was one of these cases. You're going to try factoring and reducing. So this requires you to remember how to factor x squared plus x minus 6. So x squared plus x minus 6 factors to x minus 2 times x plus 3. And if I multiply those back out, you can do this by foiling, or I like to use boxes. You check that, you'll see it indeed will give you back x squared plus x minus 6. If you need to review factoring, you should be able to factor this. As a 1 in front of the x squared, that makes this factoring pretty easy. Now that you have 2 factors on the top and 1 on the bottom, you can reduce the factors. Don't lose your negative sign. This reduces to negative x plus 3. After you reduce, you go back and try substitution again. So I have the negative of 2 plus 3. 2 plus 3 is 5, so I get negative 5. The limit as x goes to 2 is negative 5. So this here, started the circle of 2, is your answer. So we had a case where we tried substitution. We got 0 divided by 0. We factored and reduced. And then if it does factor and reduce, if you can change the form of the expression by reducing it, which we did, we found out, oh, except for the domain, it's equivalent to the negative of x plus 3. Now I try substitution again. I can go back and try step 1 again. If that works, you're done. So the answer to this one is -5. That was example 2, where we got 0 over 0 and we substituted, and we resolved it by factoring, reducing, and substituting again. Now, I got 0 over 0 for example 5 also, but there's not really an easy way to factor sine of 5x over 3x. You can try some stuff with trig identities, but we don't need to go there. I'm going to show you a different technique you can use. And when we learn L'Hopital's rule, we'll learn even another technique we could use for this one. So that's a problem where we get 0 divided by 0 and we couldn't factor. So we're going to do this in a different kind of step we'll call step 3. So case 2 of substituting and getting division by 0 is you get a number divided by 0. What that means is you're probably not going to be able to factor and reduce. So if I factor x squared over 2x plus 4, I get x times x over 2x plus 4. And I cannot reduce the x with the x because I'm terms, not factors on the bottom. 2x and 4 are separate terms. I can only do it if it was 2x times 4. So I can't reduce this one. So I have to look at another method. Well, what happens here is you are at a vertical asymptote. And three things can happen, well, several things can happen at vertical asymptotes. So vertical asymptote is a hole in the domain, and the function typically, it can go like this. It can go up in both directions as you move from the left and from the right, and go off to positive infinity. Or your function can do this thing where it drops on both sides and gets closer and closer, but never crosses that asymptote. Your limit would be negative infinity. Or it could do one of each. It could dive on this side like 1 over x does this. Okay. So 1 over x at x equals 0, the limit as x goes to 0, 1 over x does not exist because the two sides don't go to the same type of infinity. So when you have a number divided by 0, that's often what you're dealing with. So what you do with that is factoring isn't useful. You need to find the limit on the left side and the limit on the right side. And don't overthink this. You want to find a limit just to the left of x is -2. Well, if you think of a number line, is x is -2. Numbers down here have a higher absolute value than -2. So you want to pick something really, really close to -2, but just to its left. So I pick -2.001. And a number really, really close to -2, but to its right is going to be -1.999. Now, if I were picking a number close to positive 2, the left would be positive 1.999. Make sure you draw a number line if you're confused. Sometimes students get the left and right mixed up. It wouldn't actually matter for your final answer if you did that, but that's what we're going to do. We're picking numbers to the left and right of -2. So you know you're going to get some form of infinity because you're at a vertical asymptote for this. That's the rules for finding vertical asymptotes for rational expressions is if the bottom is 0 and the top is not, then you have a vertical asymptote. So you're either going to have infinity on the left and infinity on the right, negative infinity on the left and negative infinity on the right, or they're going to be mixed up. So I pick a number that's just slightly less than -2, and I substitute. -2.001 squared. That'll give me a positive number. Anytime I square a value, I get a positive number. So it doesn't really matter what this number is as long as it's not 0, it's going to be positive. And on the bottom, a 2 times a little bit more than -2 is going to be like a -4.002. When I subtract 4 from that, I am going to get sorry, this should be the limit as x goes to positive 2. I don't know why it says -2 there. This should, all right, I'm going to stop the video here. All right, pardon that brief blip, I'm back. I changed the problem on you here. That's why this is strange. That should be +4, that should be +4. So if you notice, it's +4 further up here. That's why I was looking at that saying, I'm getting a -8. I should get something. So when I evaluate 2x plus 4 at x equals -2.001, I get -4.002 plus 4, which will give me a little bit of a negative number. You can do that in your calculator. So I get a positive value over a negative value. So the limit on this side is negative infinity. So the limit as x goes to negative 2 from the left of x squared over 2x plus 4 equals negative infinity. Now I have to do the same thing on the right side. I got to pick a number a little bigger than negative 2 and see if I also get negative infinity. I might get positive infinity. I need to see. So I go down and I do the same process, and again I have that same mistake that this is 2x plus 4. I go that same process and it shows me that again the top will be positive. Negative 1.999 is slightly larger than negative 2, slightly to the right on the number line. I get a positive value on the top. Oh, and this gives me a number that's slightly less than negative 4. Remember, that's supposed to be addition. Negative 3 point something plus 4, so I get a positive there. So this limit is positive infinity. So the limit as x goes to negative 2 from the right of x squared over 2x plus 4 is positive infinity. Well, when I did the limit as x goes to negative 2 from the left, I got negative infinity. They do not match. The rule for limits is if the limit from the left is not equal for the limit as to the limit from the right, then the limit does not exist. And this is also a little bit of a review of doing one-sided limits. So the limits do not, the limit at x equals negative 2 does not exist. So because of those two things I just found, we can write the limit as x goes to negative 2 without a plus or a minus on the top, just plain old negative 2 over 2x plus 4 does not exist, or DNE, you may be abbreviating that. Okay. Example 4 was another case where we got a number divided by 0. So we're going to do the same thing. This time we're finding the limit as x goes to 1 of a rational function. So 0, for a little less than 1, I'll use 0.999. And for a number a little bigger than 1, again, I know I'm at an asymptote. I know I'm getting some form of infinity. I'm just using these numbers to find the sign of the infinity. Use 1.001. So when I put 0.999 in and subtract 3, I get a negative number. So I have a negative on the top. When I put 0.999 in here, square it, subtract it, I get a positive number. So a negative divided by a positive is negative infinity. Now, you might have noticed I factored this here. If you can factor, you should try to factor. It's pretty clear looking at this problem that you're not going to be able to reduce an x minus 3 with a 1 as your last term on the bottom. But it might be worth factoring because that makes this substitution evaluation a little easier. I could do 0.999 minus 3, and I clearly can see that that's negative. And then I can do 0.999 minus 1 squared. And oh, wait a minute, I have a number squared on the bottom. That number is always going to be positive. So it evaluates quicker, if you notice that. But otherwise, you can use your calculator to do this. So when I go down and try the limit as x goes to 1 from the right, so the limit, what my conclusion here is the limit as x goes to 1 from numbers slightly less than 1, which would be the minus sign at the top, of x minus 3 over x squared minus 2x plus 1. My conclusion is that side of the limit is negative infinity. When I do the same approach for the using 1.001, I get 1.001 minus 3, which is still negative, over, I'm gonna do it in the easy form, 1.001 minus 1 squared. But if you had substituted in like I did here and evaluated, it doesn't matter because that bottom's going to be positive anyway. You don't even need to look at the bottom. You automatically know it's positive because it's something squared. It's a number squared. This is still negative at the top, so this is also negative infinity. So the limit as x goes to 1 of the whole thing is negative infinity. So the last case we had, it didn't exist. In this case, it's negative infinity. And then for step 3, steps 1 and 2 didn't work. I couldn't factor this. The last example we have left is example 5. You're going to make a table of values. I'm going to put that in the next video because it's going to take a little bit of time with the I'm going to show you the calculator use too. So thank you for joining me, and look for part 2 of evaluating limits at a number.